Hi, I'm Zor. Welcome to Unizor Education. Well, today we will try to derive the Noether's theorem purely theoretically, pure math, nothing else. Now, why is it important? Well, as we know, Noether's theorem is something which is really opens the very fundamental properties of nature. Property of such a way that basically it was kind of a surprise, maybe I would say, for physicists, I mean big physicists like Einstein, to understand that its symmetries of our universe, like uniformity of time, for example, are the reason for conservation laws. From uniformity of time, we can derive the conservation of energy, for example. From uniformity of space, we can derive the momentum conservation. So these are very, very fundamental properties of our space where we live. And the fact that our conservation laws are not really just given to us from experiment, but follow from something which is much more fundamental, like uniformity of time, for example. Like today is basically the same time as tomorrow, or this particular space, spot in space is the same as the next one. So from this uniformity follows the conservation laws of energy, momentum, etc. So that's why it's very, very important. We are approaching much more fundamental properties of the nature. Okay, so Noether's theorem, and we're going to derive them today. I would like to say that this lecture is part of the course called Physics Plus for all. It's presented on Unizor.com. The site is totally free, no subscription, no advertisement. Sign in is optional. So it's basically pure knowledge for your consumption. And there are prerequisite courses, of course. There is a physics for teenagers. There is math for teens. There is math plus again. So all these basically are fundamental knowledges which you need to approach something obviously more advanced. So also there were 2 lectures preceding this one within the same chapter dedicated to Noether's theorem, and in these 2 lectures I have introduced certain concepts which I will very briefly repeat today, just for completeness. But basically the previous 2 lectures must be kind of learned, studied, to fully understand what I'm talking about right now. So very briefly, symmetries. First of all, symmetries are relevant to the laws of nature, especially conservation laws. And basically, what is a symmetry? Symmetry is a process, a transformation process. Like, for example, if you have a square and you draw a diagonal, both sides which square is divided into are symmetrical. Why? Because you can fold it along the diagonal and it will basically coincide with itself, right? So symmetry is a property of being the same after transformation. Okay. Now, transformation is very, very important for this concept. Now, next we were modeling motion, any kind of a movement in space and time, as transformation of coordinates. But since we are introducing the time as well, I would like actually to put time on the same level as space coordinates. Now, when I'm talking about space, I'm talking about generalized coordinates in the space. And again, this concept was introduced before, so I kind of assume that you know it. Well, in two words, it's not necessarily Cartesian coordinates. It can be polar or anything else. So that's why we're talking about Cartesian coordinates. So any set of numbers which basically characterize position in space, plus one number which characterizes the position in time. So altogether, they are time-space coordinates. And I have introduced before the concept of configuration space. Well, these are all generalized coordinates, and extended configuration space when I'm just adding one more parameter, time. So now, whatever I'm talking about space, I'm talking about extended configuration space where there is a time coordinate and, let's say, n generalized space coordinates. But I don't want actually to distinguish them. I will distinguish them in writing, but not in their rights, their level of importance, or anything like that. They are all supposed to be on the same level. Time and generalized coordinates, they're all coordinates in extended configuration space, which I usually will use something like t comma q, which is actually t comma q1, q2, etc., qn. All n generalized coordinates, and for brevity I will just use one letter q, assuming that this is actually a set of n generalized coordinates. So these are coordinates in extended configuration space. Okay, so we have introduced that. Next, the concept which you have to be familiar with is Lagrangian. So Lagrangian in typical form is a function of time, generalized coordinates, and their time derivatives. Now, in this particular interpretation, Lagrangian is not really kind of symmetrical relative to coordinates. Now, with transformation of space and time, we are changing all coordinates in extended t and q. And later on, I will introduce Lagrangian, which is more symmetrical relative to these coordinates. So far, let's just concentrate on this particular type. Now, trajectory. Again, if before we were talking about trajectory as basically a trajectory in space, well, let's say you move along the line. Now, if I will draw this, let's say this is a plane, and this is basically the trajectory of the movement, it's not really a full representation of motion, because you can move only forward, or you can move back and forward. The trajectory will be the same basically in space, but it does not represent the whole motion. To have the full motion, we are actually have to add the time parameter, and we were talking about this. So in extended configuration space, when you have not only coordinates, but also not only space coordinates, but also the time coordinates, this would be x1, this would be x2, or rather q1 and q2. Then it's not really a line within the q1, q2 plane. It will be some kind of a line in three-dimensional space right now. So if this is n-dimensional, this is n plus one dimensional thing, right? And in this particular case, you can actually represent trajectory as a function of time, and that's where you can actually put everything in such a way that geometry would really represent the trajectory. Without the time, purely geometrical representation in space does not represent the motion. you have to add this. And we were talking about this in the previous lecture about time and space. So that's important that we are talking about extended configuration space with time parameter. And now the trajectory is, it's a curve in n+1 dimensional space. Now, if we have only one coordinate, let's say we have only one line where the object is moving. Now, if you will introduce another, so let's say this is the line where it's moving, this is the q, then introducing the t, so it's not moving just like this, it will move something like this, and that means it moves back a little bit, forward a little bit, back a little bit, forward, back, again forward, significantly back, and then again forward. So that's basically represent in this case two-dimensional, because it's one-dimensional space and one-dimensional time. So that's basically what I mean about trajectory in n+1 dimensional space. It's a curve. And again, we're talking about pure geometry right now. Geometrical representation does in n+1 dimensional extended configuration space represent the motion, not just the physical place where the point object is located. We are representing its real motion. So let's say we have something like time from A to B in this case, and that basically this piece of curve represents the motion from time A to time B. Now I would like actually to do this in a slightly more symmetrical way. Now, how the curve is represented mathematically in multidimensional space? Well, usually it's represented parametrically, which means if you have coordinates, let's say t, which is one coordinate, time coordinate, and n coordinates, q1, etc., qn, then we can introduce some kind of a parameter, x, and from this parameter, position tq depends upon. So this describes where x belongs, let's say, from A to B. Now the position in the beginning is t of A, q of A. Position at the end of the motion is t of B, q of B. And in between A and B, you have this trajectory in, well, n+1 dimensional space. So back to one-dimensional space and one-dimensional time. So if you have a motion along this line, this is q, and this is t. So this is some kind of a curve. So this would be a place called t of A, q of A, and this would be, this is point A, and point B would be t of B, q of B. So x is just a parameter. It's a pure mathematical representation of any curve. If you would like to know how the curve looks like geometrically, well, you basically need, in this case, n+1 functions of some parameter. That's it. Now, if before we were talking about representation based on time asymmetrically, then the time was actually was the parameter. Now, if you really want to have time as a parameter, you can always choose x, which is equal to t, and still you will have n+1 function. One function is t of x, which is equal to x, and q of x, which is equal to some kind of coordinates. So you still have your time dependency if you want to. But if transformation actually, you see, my point is that if you have an independent parameter x, and then you do a transformation, then you transform t of x into nu t of x and q of x into nu t of x, but x is still the same. You still use the same unmutable parameter, which changes from a to b, to have a transformed curve. So from one curve you transform it to another curve, but still a and b would be the same, but the curve will be different. So that's very important to understand, that any curve, in this case n plus 1 dimensional space, can be represented with a function of some independent parameter which is defined on some fixed segment of real numbers. Maybe it's from 0 to 1000 or whatever it is. Doesn't really matter. So the curve's representation is parameterized. That's very, very important. Okay, let's go further. So trajectory is a curve, geometrical curve in extended space, and this curve represents the motion. Okay, what's next? Okay, next we're talking about transformation. Now, what I would like actually to say about transformation is that transformation can be actually different. For example, if you are moving along a trajectory, what's the transformation? Well, you're changing time. Let's say time is incremented by epsilon, which is t plus epsilon. And coordinate, let's say it's only one coordinate, also is changing to, which is some kind of a coordinate. You can do it. If you want, if you would like to have dependency on time, then that would be this type of a. So this is a motion along a trajectory. So you're just shifting the function q, which is basically given to you. You can do it this way. Now, what's actually more generic is, forget about this. All I'm saying is that certain epsilon defines a transformation of one set of coordinates into another coordinates. And right now it makes sense to talk about transformation, which is actually epsilon transformation, where epsilon is infinitesimal variable. So it's a small transformation, because we are talking about certain qualities of transformation, like being smooth. So if it's smooth, we have to differentiate it, right? And obviously we have to really consider the group of transformation, which we already did before, again in some previous lectures. It's a group of transformation. Epsilon is infinitesimal variable, and the group is characterized in such a way that t0 is equal to t, and q0 is equal to q. So 0 is a unit element of that group. And if you have two transformations, one after another, you are basically adding, you're combining transformations. That's why it's group. You can transform it back and forth, etc. So we have this particular transformation, and you can define these as functions, basically. So this is some kind of a function of epsilon and old position, and this is another function of epsilon and old position. So this is a transformation from point to point, and that's our mathematical representation of motion. So motion is change of coordinates, and motion can be a small one when epsilon is really small, or a little bigger, but right now we're talking about infinitesimal increment of position, so that's why we're talking about infinitesimal epsilon. All right. What's next? Next we are talking about something which is basically the fundamental property of our space. So we are assuming that the transformation which we are talking about is preserving certain laws of nature, or if you wish, the laws of nature are not changed by this particular transformation. Now, how do we model it mathematically? Well, the laws of nature are in classical physics, in Lagrangian mechanics, represented by action functional. So if you remember, there is an action functional which depends basically on trajectory, and its traditional is from T1 to T2, Lagrangian of T, Q, and Q prime, dt, where T is time, Q is generalized coordinates. So this is Lagrangian. Now, what's important, and again we were talking about this before, Lagrangian gives you certain trajectories. These trajectories are stationary points of this Lagrangian. So whenever we are doing this, solutions to this, which eventually leads to Euler-Lagrange equation, which is dl by dt is equal to d by dt dl by dq prime. Prime means time derivative. So this Euler-Lagrange differential equation gives you basically the stationary points of functional. So functional is a function of an entire trajectory, and obviously stationary points are certain trajectories which are basically allowed. I mean, these are only trajectories which can be chosen by an object which is moving. Again, this is all kind of old stuff. And first of all, I would like to slightly change this to be more symmetrical relative to time and space coordinates. And I would like to see what happens if transformation does not change my action functional, which means its stationary points are exactly the same. So the laws of nature are such that transformation of coordinates should not really change the real physical paths which object can take. So solutions to Euler-Lagrange equation should be the same for transformed for trajectories in transformed coordinates. They should still satisfy Euler-Lagrange equation. So that's my point. So mathematically, I will do this and see what happens. And the whole story of today's lecture is that if I will do this, I will come up with certain conservation law. So preservation of action, functional, along transformation like this. So if this transformation doesn't really change my functional, now that actually is that basically the laws of nature are, well, symmetrical relative to this transformation. All right, so what happens? Well, first of all, again, I would like to be a little bit more symmetrical in time and space. And since I'm approaching the whole thing geometrically, I should really have expressed time and space coordinates as not function of time, but function of that abstract parameter, independent parameter, where x belongs to AB. Now, why this is important? Well, this is important because if we are transforming coordinates t and q using these functions, what's really ugly mathematically that these guys are also changing. These are beginning and the end of the motion, and since I'm transforming the whole thing, I should really put whenever I put epsilon here and here, transformed my action function now in transformed coordinates. I should put this epsilon here and here and here and here and here. Now this is half of the problem, but this is a big problem. Okay, so let's just let's do this functional slightly differently, and then we will go and see what happens if it's not supposed to be changed by our transformation. Now, if my function t is, if my time t is a function of independent parameter x and q as well, now my Lagrangian t, q, and q star would be equal to Lagrangian t of x, q of x. Now, this is kind of a little bit difficult. So what is q prime is a time derivative, right? But I can put it dq by dx divided by dt by dx. Now, for brevity, I will use qx divided by tx. So index means derivative by this parameter. So these two functions, these are derivatives of these two functions. So now I can say, instead of q prime, derivative of q by time, I can put qx divided by tx. They are functions of x, of course. Now my Lagrangian is a function of x. And if you are talking about action function now, which is integral, I can put integral from, instead of doing this, t of b, right? Beginning and the end. This is my action function now of this Lagrangian. Q of x, qx, tx of x, dt. Alright? So instead of dt, I will put dt by dx times dx. So this is tx. And now I can differentiate from a to b. So I just replace the variable of integration. From integrating by t, I integrate now by x. What's the advantage? Advantage is that my limits of integration are constant now. And just to be more symmetrical, I will introduce a function L of t, q, tx, which is derivative of t by x, qx, which is equal to my old L of t, q, qx divided by tx times tx. Now, it's just change of the name. There is nothing more than that. But it looks much more symmetrical. This, I would say more symmetrical form of Lagrangian. So this is also Lagrangian, but expressed in a symmetrical way. It's really kind of easier to do it this way, because all the formulas will be much more symmetrical and, beautiful in this case. So now what I have to do is, for example, my transformation is changing from t to t epsilon, from q to q epsilon. Now my Lagrangian obviously would be also changed. And now I will talk only about this form of Lagrangian. So now my new action functional, which is depending on t epsilon and q epsilon, transformed parameters would be equals to integral from a to b of my extended or symmetrical, whatever, Lagrangian tx. These are all functions of x and dx. Now epsilon, 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 transformed coordinates. So this is my new action functional. Now, if we are saying that this action functional is not supposed to change because it represents actually the laws of nature, because it's not supposed to change because its stationary points not supposed to be changed. Trajectories are supposed to be the same. So geometrically, the set of all possible trajectories, if we change coordinates in some way or another, should not really change. Which means what? Which means d by d epsilon of the whole thing must be equal to 0. That's what's important. So whenever I'm infinitesimally changing my coordinates by transformation, by epsilon transformation, we should not change our action functional, we should not change stationary points, real trajectories which can be taken by the object. And this is the fundamental equation from which everything else just follows purely mathematically. Now, what actually should I do? Well, I mean, it's really simple. I mean, whenever you do d by d epsilon of integral, I can put integral in front and put d of L by d epsilon dx equals to 0. Now, what is d by d epsilon of function of many arguments? Well, it's L partial derivative by t times derivative of t of epsilon by d epsilon, right? Plus partial derivative by q times dq epsilon by d epsilon, plus partial derivative of by tx times dt x epsilon by epsilon plus lqx times dqx epsilon by d epsilon. So that's what full derivative by epsilon means. So times dx integral of a to b equals to 0. Now, what I will do next is, I don't want actually to do all these purely mathematical calculations. I put them all in writing into notes for this lecture. Now, every lecture has its notes, and basically what I'm doing is I'm using the integration. Now, this is all integral, remember, from a to b. So I'm doing integration by parts. I'm doing integration by parts, and using this, I'm transforming the formula basically. And there are like 3, 4, 5 lines of transformation, which I basically just refer you to notes for this lecture. It's nothing. It's pure and simple calculus. When I'm using the partial integration by parts formula, I actually derive this formula in my notes. So you will have absolutely no problem to follow this. And as a result, I have certain expression which I will put final here. Okay, it looks like the following. L by Tx times tau plus L times Qx by eta. Oh, I forgot to tell you, this thing with epsilon equals to 0, I call it tau, and this thing for epsilon equals to 0, because we actually have to take this derivative by epsilon very close to 0, that's why I put it to 0. That's equal to eta, so that's eta. Just again, for abbreviation, formula would be just a little bit better. Now integral, this is things which goes outside of integral with limits, and the rest of this would be two things. It would be would be integral from a to b L c times tau minus d por dx L tau dx tau dx, and similarly for q. Partial derivative by q times eta minus derivative by dx, partial derivative by qx times eta dx. Now look at this and look at this. Well, these are Euler-Lagrange equations. Let's talk about this one. Let me put it in more explicit. It's dl by dq. Once more, dl by dq times. Oh, I'm sorry, I put it outside of the brackets here. It's not here. Yes. Minus d by dx, dl by dqx. This is well. This is well. Sorry. This is Euler-Lagrange equation, but instead of parameter t, I'm using parameter x, and that's the only difference. Which means the whole thing, this thing, is equal to 0, as well as this thing is equal to 0. And the only thing which remains is that this is d by d epsilon is equal to 0. So my transformation does not change this. Now, if this is equal to 0, it means that if I will substitute a, if I will substitute a, and if I will substitute b, so if I will have it L tx from b plus tau of b plus L qx eta of a b minus L tx, sorry, this L of a times tau of a plus L qx of a times eta of a equal to each other, right? If from a to b is equal to 0, means the value of b is equal to value of a. But now we can change a and b in any way. Which means what? Which means that the whole thing of x, of any x, is constant. So this is basically the Noether's theorem, that this is constant. This is a law of conservation. In certain cases, whenever we are changing coordinates in some way or another, you will see that from this, and that would be in the next lecture, you will see that from this follows energy conservation. If we will talk about T symmetry, we will have momentum conservation. If we will talk about Q symmetry, etc. By the way, this is much more symmetrical representation, because again, the Q is not just the Q, it's a set, Q1, Q2, Q3. So since we are talking about integral, this is not just one value, it's value for Q1, value for Q2, etc., all summarized together. So it's all symmetrical relative to all coordinates. Coordinate T is the first coordinate, then Q1, Q2, Q3, they're all symmetrical. So these are called generators. It's a change of the coordinates at epsilon is equal to 0, or speed, if you wish. Speed of the changing of coordinate by transformation, whenever the transformation starts basically doing transforming. So it's a derivative at epsilon is equal to 0. So this is the result. This is, I skipped all the simple calculus transformations. It's all in notes for this lecture, which is on unizor.com, by the way. So this is the result. And next lecture will be, I will use this particular transformation law, the constant of this particular thing, to derive any kind of a law of conservation. Well, I do suggest you to read my notes for this lecture again, and it's actually like a textbook. Whatever I was talking right now here is presented maybe in more, I would say, smooth way in those notes. So I do suggest you to read them. So you go to unizor.com, go to Physics Plus course, find the Noether's Theorem chapter, and this is the derivation of Noether's Theorem. That's it for today. Thank you very much, and good luck.